All right, so let's look at our example again. So here is um, the differential equation that we just solved, right? And then the method of variation of parameters is to look for the answer in the form where the right-hand side is a combination of solutions of the corresponding homogeneous differential equation with coefficients that depend on t, right? And then after the long and calculation that involved several very clever tricks, we got the final answer, right? So I mean, of course we did it for a particular case, but you can I guess you can easily see that this whole logic can be generalized to I mean it just generalizes without literally any change to solve a general non-homogeneous differential equation. So what we need to have here is that if we want to find a particular solution of a non-homogeneous differential equation, we need to know the general solution of the corresponding homogeneous equation. And then we look for a particular solution in this form, and then there's going to be two equations on this u1 and u2. The first equation comes from a trick that we invented to simplify the computation, and the second equation is substituting this big y of t into the differential equation. But after all simplifications, we got just algebraic equations in u1 prime and u2 prime, and the determinant of the system is exactly the Wronskian. And then we can apply Cramer's rule to find the final answer, and here is the final answer. So now, of course, when you do this in practice, you don't really have to go through all the steps again, so you can just use the final answer. Namely, what you do is you use this equation. So you just write that the particular solution of the non-homogeneous equation is written in this form, where u1 and u2 are given by these two formulae. Okay, so let's wrap up again. In today's lecture, we learned how to solve a homogeneous linear second-order differential equation with constant coefficients. I mean, we finished all the cases. To do all the cases, we set up the characteristic equation, which is an algebraic equation, just a quadratic equation. Then we solve it, and the discriminant can be either positive, so then the solution, there are two distinct real roots, and then both of them, they appear as exponents in the solution. And then if the discriminant is 0, it means that the characteristic equation has a repeated root. So then it appears in the exponent, but also the second solution is t times the same exponential function. So, and then finally, the discriminant could be 0. So then we have two distinct complex roots. And then the general solution is formed as follows. It is a combination of cosine and sine. And inside cosine and sine, we have the imaginary part of the complex roots and times the exponential function. And then in the exponent, we have the real part of the complex roots. All right, and then if we have a non-homogeneous differential equation, then its general solution is any particular solution plus the general solution of the corresponding homogeneous differential equation. So this is just exactly the same as in linear algebra 1. Well, and finally, if we want to solve it, well, then the biggest problem here is to find, well, I guess, I'm not sure if the biggest problem, I guess it depends, but if we know the general solution of the corresponding homogeneous equation, then the method of undetermined coefficients tells us how to find a particular solution of the non-homogeneous equation. And here is how. So first you write it as a combination of um, solutions of the homogeneous equation with coefficients that are functions of t, and they can be found using this, which is the method of undetermined coefficients.